SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome back. Today we will look at some more schemes, and the two main schemes that we are going to see today is the leapfrog scheme and the Lax-Von scheme. Also, we will briefly see another scheme which is proposed by warming and beam, beam warming scheme. Okay. So, in the leapfrog scheme, as we had discussed some time back, it is because it is leaping. So, how do we take a leap? So, it is also a variance of the FTCS scheme. So, in the FTCS scheme, we have ui n is equal to n plus 1 is equal to ui n and minus lambda by 2 ui plus 1 n minus ui minus 1 n, right. So, this is unstable. And this can be written as ui n plus 1 minus ui n by delta t is equal to minus 1 ui plus 1 minus ui minus 1 by 2 delta x, right. Del u by del t equal to c del by del x, and this was forward in time and then central in space. Okay. In the leapfrogging, what you do is instead of using forward in time, you use central difference in time, central in time. So, then this will become ui, just one second, ui plus 1 ui n plus 1 minus ui n by 2 delta t. We are using central differencing in the time also is equal to minus c ui plus 1 n minus ui minus 1 n by 2 delta x, right. This 2 will cancel out, and then you can write this is ui n plus 1 equal to ui n this will be n minus 1, right, because you are using central differencing, right, minus 1 minus this will be lambda c delta t by del x ui plus 1 n minus ui minus 1, right. So, this is our scheme. Okay. So, why do we call it leapfrogging scheme? Okay. So, look at the stencil of this scheme. Okay, this is my n and this is my n plus 1. Okay. This is my line, this is my I plus 1, this is I minus 1. Okay. And because this goes from n minus 1 to n plus 1, so I have to make another line. Okay. This is my n minus 1. Okay. Now, if you want to go to n plus 1, so this is my ui n plus 1, right. This is my ui n plus 1. Okay. So, what are the instances that are participating in this? You can see this is ui n minus 1 and then ui plus 1 n and ui minus 1 n. Okay. So, this is ui n minus 1, okay, this is ui plus 1 n and this is ui minus n. Okay. So, these 4 will participate in getting the value at ui n plus 1. Okay. And interestingly, you will see that this one does not participate in this also. So, ui n does not participate. Okay. Secondly, this is a 3 time level scheme. That means, you need the, if you want to calculate that value at n plus 1, you need the value of n minus 1 n, okay, and n plus 1, right. So, basically at a given time you need 3 time levels, right. So, that means you need more bookkeeping. Earlier you could just keep on updating between n and n plus 1 and that will work, right. Now, you need n minus 1 also. So, this is a 3 time level scheme. We will talk about the stability in the, we will discuss about this shortly, and we will see that it is also stable for lambda less than equal to 1. Okay. So, that is very interesting. We just changed the time stepping from the forward in time to central in time, and our spacing also, I mean the scheme, entire scheme became stable for lambda less than equal to 1. See, this added stability, and I am not going to do that, but if you do this modified partial differential equation analysis, you will get the error which is dispersive. Okay. So, just I have written it here. So, you will get a term, this is very easy to do, like we have been doing. Okay. Just use the Taylor series and you will get an expression which is basically like this. Okay. And you can see that the first leading term that you are getting is u x x x. Okay. So, that is the third order derivative. That means, it should give you the dispersion. Okay. So, error is dispersion. That means, if you have even slight basically difference or slight perturbation in your initial condition or slight error, that will not die out. Okay. That will basically be dispersed, and that will make the scheme, I mean that will give the solution completely bad. Okay. It will mess up the solution. So, that is how the dispersion error acts. It will not dissipate any error in your initial condition. Okay. Not only error, but maybe something like something coming out of the machine, right. So, there also, if you have something that is getting into your system, that will not be dissipated. Okay. Now, let us look at the stability of this scheme. Okay. So, the scheme I have is u y n plus 1 is equal to u y n minus 1 minus lambda by 2 u y plus 1 n minus u y minus 1 n. Okay. Use our Fourier and surge. So, I will take I'll cancel this out, e to the power I phi on both the sides. So, then it can be written as g to the power n plus 1 is equal to g to the power n minus 1 minus lambda by 2 zeta to the power I phi, okay, minus e to the power minus I phi, e to the power I phi or minus I phi, right. And this will be g to the power n, because this is the nth level, right. Now, how do we do the stability analysis of the system, right? Let us simplify a little bit more. N minus 1 minus lambda per n. What is this value? This is 2y sin phi, right. Divide the entire thing by g to the power n. This is g to the power n plus 1 and g to the power n is equal to n minus 1 by g to the power n equal to minus 2 lambda I sin phi, right. Now, look, recall the definition of the amplification factor. So, G is basically g to the power n plus 1 by g to the power n. That means, that amplification factor should also be equal to g to the power n by g to the power n minus 1, right. So, you can use this definition here. This will become G is equal to, this is 1 by G minus 2 lambda I sin phi, right. So, this will make you give you a quadratic equation g square, okay, plus 2 lambda I sin phi g minus 1 equal to 0, right. So, you get a quadratic equation. Let us try looking at the stability. Okay. So, this is the equation that you are going to get, okay. And if you do the use the I mean try to find the root of that equation. So, the equation is g square plus 2g I sin phi, okay, minus 1 lambda I sin phi minus 1 equal to 0, g is equal to minus b, which is minus 2g 2 lambda I sin phi. I am solving for g, plus minus root d, so that is b square, that is 4 lambda square, and then I square phi, so that will become sin square phi minus sin minus 4 AC, so that is 4, okay, by 2 into a, then that will be 2, right. So, you can take 2 here and 2 here out, so that will become minus lambda I sin phi, and that will be plus minus, okay, and this will become minus 4 AC, that will be plus, right, there is a minus sign here, okay, this will 1 minus lambda square sin square phi. So, this is the value of g. Now, you can look at this equation also closely, okay, and if lambda is greater than 1, okay. See, if lambda is greater than 1, then this is 1 minus lambda square sin square phi, okay, this may become less than 1, okay. You can check for different phi, okay, except 0, okay, and so it may become less than 1. So, then this term will become negative. So, this is square root of something minus, let us say, some real number. So, then this is also an imaginary number, okay. So, this term, the entire g will become imaginary term multiplied by some factor, okay. So, then it will become, the g will become the your amplification vector factor will become greater than 1, okay. Only when you have lambda less than equal to 1, then this 1 minus lambda square sin square phi will be real, okay, this will be a real number, okay, square root of lambda square phi, because this term is now positive, right, and then you can do this GG star, okay. So, if you do the GG star, so this is your real part and this is your imaginary part, okay. So, real square plus imaginary square, so this will be your GG star, okay, and you can see that this will cancel out and this will GG star will become 1. So, that is, it will have no dissipation. So, your G is equal to 1, mod G is equal to 1, right. That means, this scheme will give you no dissipation for lambda less than equal to 1, right, but remember this is a dispersive scheme. So, your amplitude will not go down, okay, but this scheme may quickly become unstable if you have any error or any kind of inherent disturbance in the system, okay. So, that is the property of the leapfrog scheme, okay. And this is the stability plot that you can plot, okay. So, for example, if you have lambda equal to all the way from 0.25 to 1.0, so everything will stay in this region, okay. But as you see that if you go to lambda equal to 1.25 in some region, so this is my phi, okay, this angle is my phi, okay. So, this is phi equal to pi by 2, right. So, that will become 1. So, let us work that out, square root of 1 minus lambda square sin square phi, and lambda is equal to 1.25, okay. So, your first term will become 1 minus 1.25 square, right, and this is an imaginary number, okay. And because of that imaginary number, you will see that you have this term becoming greater than 1. So, this is becoming unstable. So, any value lambda greater than 1 will give you the unstable region, and that scheme cannot be used. So, the scheme is stable for lambda equal to lambda less than equal to 1, right. Now, we are discussing the last scheme, which is the Lax-Bendorf scheme, okay. So, what we are doing here, so if you look at your FTCS scheme very closely, the MPD of the FTCS scheme, okay. So, what we had is was it is a convection diffusion equation, okay, and it was like u t plus c u x I n was minus c square delta t by 2 u x x, right. This we derived in the last class also, and we said that because of the negative diffusion the scheme is unstable. So, what Lax and Van Dorp did is that they said that okay, we want to use the central diffusion scheme, but we are seeing that because of the negative diffusion the scheme is becoming unstable. So, what if we just make sure that we have 0 diffusion, okay, that means we will cancel out this term, okay. So, then you will get a scheme which is solving this equation, but cancelling out this negative diffusion term, okay. So, this is what the scheme is. So, now we are proposing a convection I mean for the convection term we are proposing a scheme which looks like this u t plus c u x. So, this is in the discretized domain, you can call it, okay. This is not the PD, but this in the discretized equation, okay. So, this is I and n, okay. So, then you can write the time derivative like this: forward in time, central in space, and this theta is the diffusion coefficient or diffusion number which multiply to your u x x discretized scheme, right. So, if you compare with this FTCS scheme, we have to just balance out this term. So, your theta will become c square delta t by 2, right. So, that is if you so finally your scheme will become like this, okay. So, this is our scheme for solving. Remember, we are still solving del u by del t plus c del u by del x, okay, but we are solving in a way that my del u by del t is done using the forward in time, this is done in central in space, okay, and then we have an additional diffusion term, okay. This is my additional diffusion term, which is just making sure that the scheme becomes stable. We will look at the stability of the scheme very soon, okay. So, just we replace the theta by equal to c square delta t by 2, okay, and then you work that out, multiply by delta t and put in this form, you will see that your theta becomes delta square, right. This is theta by 2, okay. So, this is your Lax-Van Dorp scheme. This is scheme called Lax-Van Dorp scheme, and unlike the Lax-Frederick scheme where the order of accuracy decreased, okay, here the accuracy is of second order. So, your accuracy remains maintained, okay. You can go back and do the modified PD analysis, and you will see that the first term that you are getting is the dispersion term, okay. C delta x square by 6 1 minus lambda square u x x x. This is also due to the fact that we are cancelling out this u x x term that is coming through this additional diffusion term, okay. So, this is a dispersive equation, okay, but I mean what you can do, you can derive your own scheme, okay. So, here instead of lambda square you can use some other value of the diffusion, or and you can check whether the scheme is stable or not, right. So, this is just balancing out. If you put more than lambda square, then what will happen? It will be more dissipative. So, you will have a dissipation error in the leading term, okay. If you put your diffusion number less than lambda square, then what will happen? The scheme will become unstable. Let us see all those things. Let me go through the slides itself, okay, in the interest of time. So, we are doing the stability analysis of this, okay. So, this is my g to the power n plus 1, this is g to the power n, this is e to the power I phi, this is e to the power minus I phi, okay, and then these 3 terms, this is I phi, minus I phi and minus 2, right. Now, you use this e to the power I phi minus e to the power minus I phi is basically 2 cos phi, okay, and here you can see that I have changed the notation to alpha. So, for the Lax-Van Dorp scheme, we are alpha equal to lambda square, right, as we see as we show in the last slide, but we are doing it for a general alpha. We are trying to see that up to what diffusion number we can use, right. can we use lower than this or greater than this? What happens if you use lower than lambda square or greater than lambda square? So, what happens, right? So, this is my 2 cos phi, and this one if you look at, so if you add this I phi plus e to the power minus I phi minus 2, that will be 2 I sin phi minus 2, okay, and no, this is negative. So, this is 2 I sin phi, okay, that is correct. Okay. So, you can multiply that with, so that will become, let me just do it here. No, we are adding this, right. So, this will be cos phi. And you are subtracting this, so that will be 2 I sin phi. Okay. So, put it there, this is 2 I sin phi and the lambda is there. So, this will become lambda I sin phi, and this is 2 cos phi minus 2. So, that will become alpha cos phi minus 1, right. 2 will get cancelled out, and if you take the magnitude of this amplitude factor g g star. So, this is my real part and this is my imaginary part, okay, lambda sin phi. Okay. So, you will have this equation, okay, real square plus imaginary square, and if you put alpha equal to 0, okay, that means this entire term goes to 0. So, this scheme is forward and center in space, and you will get the recover the amplification factor, which is 1 plus lambda square sin square phi, which is greater than 1, and this is unstable as we know already. Okay. Now, let us analyze when alpha equal to just lambda square, right, that is your lax Van der Waals scheme, right. So, when alpha equal to lambda square, you can put the value here lambda square sin square phi, okay, and then you can basically simplify it, okay, and we say that the g g star needs to be less than 1 for stability. So, this entire term should be less than equal to 1. So, the 1 will cancel out, you will have a expression which is lambda 4 1 minus cos phi square minus 2 lambda square 1 minus cos phi and lambda square sin square phi. Take the 1 minus cos phi out, right. How we can take that out? Because sin square phi is 1 minus cos square phi, which is basically 1 plus cos phi 1 minus cos phi, okay. So, take the 1 minus cos phi out. So, this is lambda to the 4 1 minus cos phi minus 2 lambda square plus lambda square 1 plus cos phi, and that will become lambda to the 4 1 minus cos phi, and this is minus lambda square 1 minus cos phi, right. So, take the 1 minus cos phi again out, okay. So, that you will have lambda 4 minus lambda square is less than equal to 0, or lambda 4 is less than equal to lambda square, that means lambda is less than equal to 1, okay. So, this is the stability if you have a lax Van der Waals scheme, which is alpha equal to lambda square, okay. Now, if you can, what you can do, you can solve for general alpha, means not the lax Van der Waals, not the FTCS, but we are just adding some arbitrary diffusion, right, and see what is the value. So, we will get a quadratic equation, okay, which will be like this, and you have to solve for alpha, okay, and you will see that the scheme is stable when alpha is greater than lambda square, which is obvious because lambda square is just the right amount of diffusion for to make this scheme stable, right. And if you add more than lambda square, then scheme will become more and more dissipative. If you add less than lambda square, then it will just become unstable, right. So, this scheme is stable for lambda square less than equal to alpha and less than equal to 1. So, you might want to add little bit more than lambda square, so that the scheme becomes more and more stable. It will have just a little bit of dissipation in the scheme, right. So, this is how you can derive the scheme. You can also look at the polar plot, okay, or the Argand plot. So, basically what we are doing. So, this is the expression that we had earlier when we derived. So, g is equal to 1 plus, so real part is 1 minus lambda square, this 2 term plus lambda square cos phi, and the imaginary part is lambda sin phi, right. So, when we had like cos phi minus sin I sin phi, okay. So, then we had the polar plot, which was a circle, right, with a radius 1, right. Now, let us say we have cos phi 1 plus cos phi minus I sin phi. So, then you will have basically circle which is at 1, okay, and it will become like this, right. Now, let us say that I have 1 plus cos phi minus I lambda sin phi, okay, then it is an ellipse, right, which depends on lambda, your radius is 1, okay, major axis is always 1, but minor axis depends on lambda, right. So, this is my lambda and this is 1, right. So, here what we have? We have in the real term we have 1 minus lambda square. So, that is where my real axis will be, and 0, okay, and what is the radius? Okay, so, radius is lambda square and lambda, right. So, this is my radius of the major axis and this is the radius of the minor axis. So, you can go ahead and plot this. Okay, I think I have plotted it here. Okay, yeah. So, once again I have something centered at 1 minus lambda square, radius is, just let me see, lambda square, the right hand side is lambda square, this is the real axis, okay, and the imaginary axis is just lambda, okay. So, you can see that if your lambda is equal to 1.25, okay, so your center is just psi of 1, okay, this is my 1 minus lambda square, okay, and my real axis is lambda square. So, this is smaller than 1 and this is just your lambda. So, this is value of 0.25, right. You keep on increasing, let us say you go to 0.5, okay. So, this is minus 1 minus lambda square and this is minus, this is the value which is 0.5 and this is 0.5 square, right. So, this is all ellipse, okay. Similarly, you can go till lambda equal to 1. So, when the becomes lambda equal to 1, this becomes a unit circle, because lambda square and lambda both are equal to 1 and this is 1 minus 1 0, this is your center, right. So, their radius will be, the g will be equal to 1. All other cases your amplification factor is less than 1, right. You can take anywhere here or anywhere here, it is less than 1. If you go to lambda greater than 1.25, okay, you can see that now you have regions which are going outside that stability region, outside the circle, and in this case g is greater than 1, okay. This is again cannot be used, okay. So, last scheme that I am going to introduce is the beam warming, and I will not have a lot of discussion. I want you to go back and work on this. So, this is like the lax one of scheme, okay, but you will have the second order upwind term for the advection term, okay. So, instead of using and also the dissipation term also you will have this upwind term. So, these are all upwind schemes, okay. You can see the terms which are I minus 1 and I minus 2. This is also I minus 1, I minus 2, okay. Here in fact, there is a variant of beam warming scheme where you can use just I and I minus 1, right. So, for both the convection and the artificial diffusion that we are adding, the numerical diffusion that we are adding, okay, we are using the upwind scheme, okay, and you can verify that the order of the scheme is delta t square, delta x square, okay, and the leading error is the dispersion error, that also you can verify, just do the MPD analysis, modified PD analysis, and the one way to derive it is basically take your time derivative equation, okay, and replace all your time derivative with your spatial derivative, okay, and then collect these terms, right. So, this is ui n plus 1 is equal to ui n and plus delta t uti n and plus delta t square by 2 utt in, okay. So, this will become ui n minus delta t is minus u delta x, right, minus c u x delta x, okay, I n and plus delta t square by 2 is basically c square u x x, okay, and we are looking for an expression for. So, this is your beam warming scheme, okay. What you need to do is you find u x I n derivative using a suitable scheme and u x x I n using suitable scheme. So, the one I was proposing, this is the backward differencing, okay, with 3 stencils I minus 1 and I minus 2. Here also this is I minus 1 and I minus 2, okay. So, you can derive this beam warming scheme, okay. And one interesting thing that I will discuss and close the class today is that for this scheme you can note that the stability region is up to lambda equal to 2. Okay. For all the schemes that we have discussed so far, the stability was lambda less than equal to 1. Okay. But this scheme is stable up to lambda equal to 2, and that you can see clearly in this polar plot, and you can see there are some overlapping regions here. Okay. So, this is basically your lambda equal to 0.5, this is 1.5, okay, and this is both for lambda equal to 1 and lambda equal to 2, okay, this line. Okay. If you go more than 2, then your so this is my center, so this G becomes greater than 1. Okay. So, there are some schemes which has the stability limit greater than 1 also. This is what we learned from this. We can have another variant. Okay. This is variant 2 where we are just using ui minus 1 by delta x. So, this is my first order scheme here and the upwind. Okay. So, this is the so final scheme becomes delta t square delta x square. It also there is uxx error, and it has the same stability limit as earlier. That means it is stable up to lambda less than equal to 2. Okay. So, these are the schemes that we have discussed today. Okay. Yeah, lax band drop beam, arming and so on and so forth. Please go back and derive the stability limits for all these schemes, as well as derive the modified PD equation, I mean modified partial differential equation, and look at the properties of all these schemes. In the next class, we will discuss some more schemes for the nonlinear problems. Okay. And finally, we will see how all of these schemes behave for a linear problem and for a nonlinear problem. Okay. So, with that we will stop today. Thank you very much.